Hi everyone. First of all, I would like to thank the organizer for inviting me to give a talk at this nice conference. Today I'm going to talk about non-strictly convex divisible convex sets. There will be two talks. This is joint work with Gabriele Viaggi, which, by the way, is one of the organizers of this topic on Anosov groups. Actually, this talk won't be so much about Anosov groups. Also, I would like to thank Theodore Weissman, for the pictures, the videos I'm going to show in this talk. So before talking about divisible convex sets and non-strict convexity, I would like to recall the basics, in particular, a particular model of the hyperpublic space, the Klein model. So remember, the Poincaré model is a unit ball in RD endowed with the Riemannian metric given here, dx1 squared plus dxd squared over 1 minus the radius, the squared, everything squared. And in the Poincaré model, geodesics are arc circles meeting the boundary orthogonally, and the group of isometries acts transitively. The Klein model is also a unit ball of RD, but it's not the same model. Maybe the most striking feature is the fact that geodesics, instead of being arc circles, are straight lines. In fact, this model doesn't really sit in RD. Actually, it's better to see it in RPD, the real projective space. Where RD sits as an affine chart. In this, so the group acting on the projective space is PG LD plus 1R, and the stabilizer of the disk, the above disk, is PO D1. It acts also transitively on the disk, and this disk also provides a model for the hyperpublic space in the sense that we have a bijection between the two disks, which is equivariant with respect to an isomorphism between the two group actings. There is a nice formula that gives a distance, but I won't need it, so I won't recall the formula, but just so you know, there is a nice formula to give the distance in this model. Let us now consider a surface S with a hyperbolic structure. So, as many of you might already know, a way to define a hyperbolic structure is to give shards. So our surface is covered by open subsets, which are in bijection with open subset of HD, in such a way that if we have two shards that meet, then there is the associated change of chart belongs is an isometry of HD. Another way to describe a hyperbolic structure on the surface is through using the universal cover. It's giving a developing map that is equivariant with respect to a certain representation of the fundamental group rho in POD1 called the holonomy representation. since here, if we use the Klein model on the right, we can see that the hyperbolic structure naturally gives rise to a projective structure, right? We have charts. Our charts goes into the projective space, and the change of charts or projective transformations. And what we are going to do now is we are going to deform our hyperbolic structure into a projective structure which is not hyperbolic anymore. And to do this, we are going to use a bending procedure. So let us consider the following curve gamma that cuts S into two, one whole tori S1 and S2. And so the way the deformation works is so charts which are entirely contained in S1 or entirely contained in S2 are not modified. The only thing we change are charts that meet gamma. So typically, if we have a chart like that sent to such open subset, then the new charts for the new projective structure is obtained by stretching just one half of the chart. So stretching using the following map of RP2. Ft with the parameter t greater than 1. It sends a point of the affine chart R2 onto the point t, x, y. So here we have a point P. It is sent to point Ft further on the right. And the left side, the left part of the affine chart remains unchanged. Okay, if we try to see this bending procedure through the other description of the structure, meaning using the developing map and the holonomy, we get the following. First, so remember there is a famous presentation of the pi1, from the group of S with 4 generators, alpha, let us call them alpha, alpha prime, beta, beta prime. Okay. So what does the bent holonomy becomes? Okay. The new holonomy is actually quite easy to express. So the image of alpha remains the same, and the same for beta. And the holonomy of alpha prime and beta prime gets conjugated by Ft. Okay. Now, what about the developing map? So first of all, we need to describe the universal cover S tilde as a union of copies of universal covers of S1 and S2. So in the Poincaré model, it gives the following. We have here on the left the first copy of S1 tilde. Just put a 1 to say first copy. And here a copy of S2 tilde. And all around the first copy of S1 tilde, adjacent to it, we have infinitely many copies of S2 tilde. Say S S2, 2, like that, and likewise around each adjacent to S2 tilde, each copy of S2 tilde, we have many copies of S1 tilde. Etc. Okay, and each time we have a copy of S1 tilde or S2 tilde, there are many other copies adjacent to it. So this is in the Poincaré model. In the other model, it's the same thing, except that things are much harder to see. Because everything sort of gets flatter and smashed along the boundary, unfortunately. But we have the same phenomenon. And now the bent developing map looks like that. So the S1 tilde remains unchanged. And then all the other copies of the universal covers of S1 and S2 get stretched or compressed. For example, the first copy of S2 tilde gets stretched by Ft here. This other copy of S2 tilde adjacent to the first copy of S1 tilde gets stretched not by Ft, but by a conjugate of Ft. This copy of S1 tilde adjacent to the S2 tilde so is of course first stretched by Ft and then compressed by Ft minus 1, by a conjugate of Ft minus 1, and so on. So each time we cross one of those yellow geodesics, we get alternatively stretched by a conjugate of Ft and alternatively compressed by a conjugate of Ft minus 1, Ft inverse. And the result is the following. Fact, I think I should attribute it to Troy Goldman. The image of the new developing map is an open, convex, and bounded subset of R2. And the new holonomy is discrete subgroup of PGL3R. It preserves, of course, the convex subset above and acts properly discontinuously and co-compactly on it. And we say that it divides it. And maybe another remark to make the link with the topic of this conference, which is of this sub-conference, which are another groups. So maybe I can attribute this to Laborie. The representation ρT is Anosov. And actually, the reason why it's Anosov, one way to see it is because you actually have a very natural geodesic flow associated to the projective structure, which is Anosov. A flow that follows geodesics for certain metric on the convex subset, def t s tilde. Okay, let's have a look of how those convex sets vary with t, thanks to a nice GIF made by Theodore, by Teddy, where you can see t varying. So thank you. Yeah, by the way, maybe I should mention, Teddy actually wrote a very nice program that is available on his website that you can use to drawings or computations in high public space or in projective space to computations with representations of discrete groups. I recommend having a look. I used it. I mean, Teddy helped me to use it. He almost did all the work actually to produce other GIFs of other kinds of bending that we will see in the next talk. Okay. Cool. So now what is a divisible convex set? A divisible convex set is an open convex bounded subset of an affine chart of some projective space RPD. I forgot to say this bending procedure above actually it also works in higher dimensions. Just that instead of gamma, you will have hypersurface, totally just hypersurface. So RPD, which is such that there exists a discrete subgroup of PGLD plus 1, or so often we call this subset omega in the group gamma. Discrete that divides omega. And to finish this talk, I would like to present a bunch of examples, which actually you can be seen as a sort of rough classification of all divisible convex sets. One important feature of divisible convex set is that it's often hard to produce examples. Okay, the first example are the ellipsoid, which are isometric to hyperbolic space. The fact that those are actual example are divisible is not so trivial. So in dimension 2, I think we can cite Poincaré maybe somewhere at the end of the 19th century using combinatorics. So dimension 2. And then more generally, the techniques, so it's due to Zigo in 51 using arithmetic methods. Okay. So as we saw, it's not the only example of divisible convex sets because one can use bending to produce new examples. This bending procedure is due to Johnson-Milson. And I should also cite Benoit. So in 84, I believe, yes, a bending procedure which works in any dimension, produces example in any dimension. But there are other older examples of divisible convex sets actually that are in some ways closer to the ellipsoid in the sense that they are symmetric. So what does it mean? It means that the group, the stabilizer of omega acts transitively on omega and is a semi-simple algebraic subgroup of PGLD plus 1, or so typically in this, so the example I was referring to is the projective model of symmetric space of another group SLN. And it also works, there are also examples with SLN-C or SLN quaternion or SLN3 octonion. Here, the fact that those examples are divisible is due to Borel in 63 using arithmetic method. Another way to construct divisible convex sets is using two smaller divisible convex sets. So if we consider a point, which is a divisible convex set, and a disk, the convex rule of those is also a convex set, divisible convex set. And in this case, we say omega is reducible. And in the other case, omega is irreducible when you cannot write it as a convex rule. So let's go back to the case of irreducible divisible convex sets, which are non-symmetric, which don't belong to the list either of ellipsoids, either of projective model of SLN-R, SLN-C, quaternion, etc. In this case, so the situation is quite different to symmetric case because the stabilizer is now discrete and Zariski dense in PGLD plus 1. This is a result due to Ivanov. And moreover, Benoit showed that in the first case, the example produced by bending are always strictly convex with C1 boundary, and more importantly, maybe from the point of view of this conference, the group gamma is always Anosov. And as before, it's Anosov because actually we have a natural geodesic flow, which is Anosov in the sense of dynamical systems. Example, which are strictly convex, so it can be produced by bending, were actually known before. There were other construction before due to Katz-Weinberg in dimension 2 using Coxter groups in 67. Actually, their construction also worked in dimension 3, 4, 5, 6, maybe something like that. And the bending procedure allows one to go to arbitrary dimension. There are other interesting examples by Kopovich in 2006 using bending procedure. And so the remaining question is, does there exist example where gamma is not Anosov? In which case, actually, so Benoit proved that omega has to be also non-strictly convex with non-C1 boundary. And the answer is yes. If Benoit found example in 2006 using Coxter groups. And it works in dimension 3, 4, 5, 6. And its examples are not strictly convex because the omega admits properly embedded triangles. So triangles whose boundary is contained in the boundary of omega. So there are segments in the boundary of omega because of that. Later on, other kinds of examples were found out, but always in dimension less than 6 by Ballast and Ziegler-Lee using deformations in dimension 3, and then Choi-Lee-Markey in dimension 4, 5, 6. And actually also the Ludovic's Marquis thesis gives a lot of examples in dimension 3 as well, using Cox groups. And our contribution with Gabriele is that there exists non-strictly convex, non-symmetric, divisible convex sets in any dimension. At least 3. So they cannot exist in dimension. Oh, sorry. At least 3. They cannot exist in dimension 2 actually. And the method used is again bending. So my goal for the next talk is to talk about this construction, bending construction, and show nice pictures. Thank you for listening. I hope you found this topic interesting enough so that you're going to listen to the second talk.